In the previous lecture, we calculated the Fourier transform of rectangular function, and now in this lecture, we will calculate the Fourier transform of triangular function. And we have taken the general case of triangular function and we have represented the function by xt. So the time domain signal is xt and we will calculate its Fourier transform x omega. And we know the triangular function here can be represented using the ramp signals, and this implies we can use the method of differentiation. So we will differentiate this waveform till we have the waveform which is the combination of only impulses, and once we have that waveform we can easily obtain the Fourier transform. So let's quickly differentiate xt and have the waveform of dxt over dt, and we know dxt over dt will give us the slopes of signal xt. So we will focus on the calculation of different slopes we are having in this particular function. So first we will identify how many straight lines we are having here. The first straight line is from minus infinity to minus tau. Then the second straight line is from minus tau to 0. The third one is this line from 0 to tau, and the fourth one is from tau to plus infinity. And if you look closely, you will find the first line is having the slope equal to 0. So dxt over dt will be equal to 0 from minus infinity to minus tau. And after this, we are having this line and it is making an acute angle with time axis in anti-clockwise direction. Therefore, the slope will be positive and the magnitude of the slope will be equal to a divided by tau. So we will have a slope equal to plus a divided by tau. So this is how the waveform will look from minus infinity to 0. From 0 to tau, we are having the third straight line, and this line is making an obtuse angle with time axis. Therefore, the slope will be negative and the magnitude of the slope will be equal to a divided by tau. So we will have minus a over tau as the value of the slope. So from 0 to tau, we are going to have the waveform like this. After this, from tau to plus infinity, the line is making 0 degree angle with time axis. Therefore, the slope is equal to 0. So from tau to plus infinity, we are having 0 slope. And finally, the waveform of dxt over dt will look like this. And you can clearly notice that we are not having impulses present in this waveform. So we will differentiate it one more time and we will get the waveform of 2 times derivative of xt. So let's quickly differentiate the waveform, and this time we are having 1, 2, 3, 4, 5, 6 and 7 straight lines. From minus infinity to minus tau, slope is equal to 0. From minus infinity to minus tau, slope is equal to 0. After this, you can see there is upward level switching. So the slope is equal to infinity because the line is making 90 degree with the time axis, and infinite slope we represent by taking an impulse, and the weight of the impulse is equal to discontinuity, and discontinuity is equal to a over tau. We are having the positive sign here because there is upward level switching. And after this, for the third line, the slope is again equal to 0. The slope is again equal to 0. Now when t is equal to 0, there is downward level switching and the amount of discontinuity is equal to a over tau minus a over tau. This means 2 times a over tau. So we will have an impulse with more weight, 2 multiplied to a over tau, and the sign we will have is negative because there is downward level switching. After this, for the fifth line, again the slope is equal to 0. So from 0 to tau, slope will remain 0, and when t is equal to tau, there is upward level switching. Discontinuity is equal to 0 minus a by tau. So we will have an impulse with weight equal to plus a over tau, and the last line is having the 0 slope. Therefore, we will have the waveform like this from tau to plus infinity. So finally, we are having the waveform which is combination of impulses, and from here we can easily calculate the Fourier transform of xt. So let's quickly write down the two time derivatives of signal xt in terms of impulses we are having here. There are three impulses. The first one is a over tau delta t plus tau. We have a over tau delta t plus tau. The second one is equal to minus 2 a over tau delta t minus 0, minus 2 a over tau delta t minus 0, and the third one is equal to a over tau delta t minus tau, a over tau delta t minus tau. I will take a over tau common from the three impulses. So we have 2 times derivative of signal xt equal to a over tau inside the bracket delta t plus tau minus 2 times delta t plus delta t minus tau. Now we will perform the Fourier transform on both the sides. On the left hand side, we will have j omega whole square multiplied 2x omega, and on the right hand side we have a over tau inside the bracket. The Fourier transform of delta t is equal to 1, and the Fourier transform of delta t plus tau using the time shifting property is equal to 1 multiplied to e power j omega tau. Similarly, 2 delta t is having the Fourier transform equal to 2, and delta t minus tau is having the Fourier transform 1 multiplied to e power minus j omega tau. So this is what we have after performing the Fourier transform. J omega square we can write as j square omega square. J square is equal to minus 1, so we can write minus omega square, and we will divide both the sides by minus omega square. So we will have x omega on the left hand side, and on the right hand side we will have a over minus omega square multiplied to tau inside the bracket e power j omega tau plus e power minus j omega tau minus 2. We can write e power j omega tau plus e power minus j omega tau equal to 2 times cos omega tau. So let's replace this by 2 times cos omega tau. We will have 2 times cos omega tau minus 2 in the bracket, and after this we will use the property of trigonometric ratios. But to use the property we need to take 2 common. So we will take 2 common, and we will have 2 times a divided by minus omega square tau cos omega tau minus 1, and if we take this negative sign inside the bracket, then we will have 1 minus cos omega tau. So we will take this negative sign inside the bracket, and we will have 1 minus cos omega tau. We can write 1 minus cos omega tau equal to 2 times sine square omega tau by 2. So the Fourier transform x omega is equal to 2a divided by omega square tau inside the bracket 2 times sine square omega tau by 2. I will take this 2 outside the bracket. So we will have the Fourier transform equal to 4a divided by omega square tau multiplied to sine square omega tau by 2. Now I want to write the Fourier transform in terms of sampling function. Therefore, I will multiply the right hand side by omega square tau square by 4 and divide it by omega square tau square by 4. So we can write the Fourier transform x omega equal to 4a divided by omega square tau. Inside the bracket we can write sine omega tau by 2 divided by omega tau by 2 whole square multiplied to omega square tau square by 4. This 4 and 4 will cancel out. Omega square will cancel out. Tau will cancel out with 1 tau here, and we are left with a multiplied to tau sine omega tau by 2 divided by omega tau by 2 is equal to the sampling function. So we have sampling omega tau by 2. We are having square here, so we will have the square of the sampling function. So in this way we have obtained the Fourier transform of the triangular function. Try to remember this Fourier transform because this is the Fourier transform of the standard signal. So this is all for this lecture. If you have any doubt, you may ask in the comment section.